So let's start first with some basic ideas of how we would go about studying galaxy evolution. And first of all, galaxies have to evolve for the simple reason that they're made out of stars and stars evolve. But moreover, they're not in isolation, there are galaxies all around them, so merging and encounters will happen no matter what. And so you expect that these two generic processes of assembling the mass together, that's just Newtonian gravity, and then converting gas into stars and then stars making energy, are two inevitable and probably somewhat related processes because merging can stimulate bursts of star formation. And since most of the mass is dark matter, this is not something we can observe directly. And also it takes 1 billion years to digest a galaxy in a merger. But on the other hand, we can model it really easily. The opposite applies now for star formation. We don't actually understand star formation all that well, so therefore we cannot model it really well, but it's easy to observe. So first, it's interesting to ask the timescales on which this can happen, right? Galaxy free fall timescale, or rotational period, if you will, is of the order of a couple hundred million years. And massive stars, which do a lot of action, are tens to up to 100 million years lifetime. And we also think that active galactic nuclei, like quasars, go in spurts, which are about same order of magnitude. And about 1 billion years is what it takes for proper merger to complete, and then we have about 12, 13 billion years for galaxies to evolve. And so there are several different ways in which you can try to study this. You can begin with Milky Way, with the fossil evidence in form of stellar population and dynamics and so on. You can look at nearby galaxies other than Milky Way and look for systematics like those correlations that we were studying before. And the most direct thing, of course, is to look far away and see what galaxies were doing. And since the speed of light is finite, the further away you look, the deeper in the past you look. So it's like a built-in time machine. Just by looking far away, we can tell what was going on in the past. And cosmological principle is generalization of Copernican principle that the universe is the same everywhere. So that's a fair sample. So there are two parts to modeling of galaxy evolution and formation. First, assembling of the mass, and that is routinely done now with large computers, a lot of dark matter particles, maybe stars, just Newtonian gravity in an expanding space. You let it go, and it produces structures just like those that we see. So there is no mystery there. And then, of course, there is evolution of stellar populations. And we understand stars fairly well. We may not really understand star formation all that well, but once you make stars, we know how they evolve. And there are all these isochrons on HR diagram and so on. So there are plenty of movies that you can find on the web. Someday I'll link some of them to the web page. And you can see bits and pieces flying together and merging and creating ever bigger galaxies. And at any given time, it kind of looks the same, but on different scales. So early on, there's a lot of small pieces within some volume. But then later on, those have merged. But if you zoom out, look at larger volume, it's going to look exactly the same as the other one. So it's very self-similar evolution. And people now do simulations with literally billions of particles. This is one of the large ones called the Millennium simulation. And you see this interesting mess of filaments and knots. Turns out that, well, dark matter or any matter, when it collapses under gravity, will naturally make such structures. We'll talk a little more about this when we talk about formation of large-scale structure. And then there'll be dense spots in intersections of these filaments, and that's where galaxies will form. So you can start from some large redshift, where things are fairly uniform. You have just slight non-uniformities, which serve as seeds of galaxies, which then accrete more material. And then as time goes on, you get the density contrast increasing, and the scale there gives you spatial, the bar gives you spatial scale. And then as time goes on, these knots, which are really galaxy halos, keep growing and growing. And at zero redshift, you can match them to what's observed, at least in terms of dynamically inferred distribution of dark matter. So this has now been done very extensively on all kinds of scale, like whole universe scale, just the Milky Way scale, and so on. And so this is, if you had eyes that could see the dark matter, this is maybe how Milky Way would look like. There'd be a whole lot of little tiny dark halos that didn't get absorbed yet. And those might be really small dwarf galaxies that are eventually going to be consumed through tidal friction. And so the other aspect of this is stellar evolution. And again, here is HR diagram, which we understand fairly well. So you can say, convert a bunch of mass of gas into stars, according to some formula, and then just let it age, and we know which way stars will go. Now, interesting thing to remember is that on the upper main sequence, luminosity scales as a fourth power of mass. On the other hand, there are fewer massive stars than low-mass stars, and to first approximation, it goes as inverse second power of mass. So fourth power wins over inverse second power, and therefore the most massive stars will dominate the luminosity even though there are few in the number. And because those are the bluest stars, the young stellar population will also tend to be blue. And so those are generic expectations. And they would also evolve very quickly and then become redder as the main sequence turn-off peels off to ever smaller masses. So we know how to make models of evolving stellar populations. And we expect generically that will be always dominated by the stars around the main sequence turn-off, because those are the most luminous ones and most numerous ones available at any given time. And because they're relatively small in number early on, there'll be big fluctuations of that. The key assumption that one has to make, and this is purely an assumption, this is not something you can infer easily from data, is what's the history of star formation? Do you do it all at once, like a delta function? Do you do it constant over time or anything in between? And there is more or less everything in between. And we believe that ellipticals and bulges are best fit if you assume that most of star formation happened very early on, within the first billion years or thereabout, and then you just let them evolve passively. Whereas in these galaxies, star formation keeps going on all the time. So you have a mixture of stars of all different ages. Like in solar neighborhood, there is a range from 0 to maybe about 9 billion years. And we're kind of in between. So this is the type of model spectra added over all the stars in some evolving galaxy are. And you can see the time steps are labeled. You can't see them very well. And the youngest ones are at the top, so yes, they're most luminous, but also you can see that they're bluest, and then as galaxy ages, you start losing these stars that dominate UV, and red giants keep showing up, so the color changes to the red. So generic expectation is that as galaxies age, they get dimmer and they get redder. And in fact, that is the case. So the simplest thing you can do is look at colors of galaxies, and color, as you may recall, is logarithmic ratio of the fluxes in two filters. And here it's ultraviolet to blue and blue to visual. And if you plot those distributions, they're by model, there is a kind of narrow spike of very red stuff, that's ellipticals and bulges. They have very small spread of colors because the color doesn't change much at large ages. And there is a very broad range of younger stuff, this bluer distribution. So that all seems to make reasonably good sense.